used by Square D at the time were not subject to ground fault protection. However, what happened in the industry and what happened in the United States is the demand for power continued to grow all throughout the 1970s and 1980s, including today. For example, in 1985, the average ampacity of our power systems, of all of our equipment, was 1,200 amps. Of our industrial, commercial facilities, equipment that we manufacture in our assembly plants, the average ampacity of, say, a switchboard, switchgear, was 1,200 amps. Consequently, required to have ground fault protection. In 1990, that ampacity increased to nearly 1,600 amps. In 2000, it increased again, nearly 2,000 amps. For example, today, 2009, the Square D company manufactures as a standard product 6,000 amp switchboards. Very, very common. So you can see the trend over time has dramatically gone up. But at the time the National Electrical Code required ground fault protection, it was very, very low. Very few people had ground fault protection because most of the facilities were not above 1,000 amps and consequently weren't required to have ground fault protection. But it didn't take care of the ground fault issues. By the 1995 code, excuse me, back up a second. Yeah. Yeah. We're back to 1 o'clock, or 1:30. Okay. Well, he came in here for just a minute while you were gone. Oh, okay. And I said, well, I thank you for sending out the notice for the change, and you want to know what changed. So, okay, we're back to 1:30. All right. Good. All right. All right. Ready?
We're at 51.
All right. Again, beginning in the mid-60s, the National Fire Protection Association began to receive numerous reports of fires, destruction, damage, deaths, injuries due to arcing ground faults. This is direct correlation to our systems in the United States being converted from ungrounded systems to solidly grounded systems. The National Electrical Code responded via the Fire Protection Association number 70, which is the National Electrical Code, and required ground fault protection to be required on power systems where the voltage was higher to ground, 150 volts to ground or higher, and 1,000 amps. Now, in 1971, the average ampacity of a power system was less than 1,000 amps. Consequently, very few facilities had ground fault protection unless they were sized 1,000 amps or higher. Now, that would require you to have ground fault protection. But during the next code cycle in 1975, it required you to have certain settings. For example, you had to have specific size settings for the ground fault protection, where the first code in 1971 did not establish settings. In 1975, they did establish settings. But because one of the reasons that the amount of damages that were occurring were not going down due to the institution of code cycles or requirement for ground fault protection in 71, they were actually going up. Two things affected that. One, there was no specifications about functionality or requirements, where there's time delay settings or maximum settings. So the code institutes settings requirements in 1975. The other thing that was happening between 1971 and 1975, the power systems demand in the electrical industry were going up in size. So there were a lot more systems that would qualify and have damaging ground fault. As a large transformer goes up in size, the electrical services goes up in size, the available ground fault energy also goes up dramatically. However, in 1978, there was a change to the National Code that requires you to test it. What was happening is that we were finding that systems were being installed in the field but really weren't functioning. Either they got damaged in shipment or the electrical contractor, fairly new to the technology, didn't hook up shipping splits or connections in the field. So in 1978, you were required to test the systems to verify that they were happening. Now, the thing to remember that's going on correlation to this is how bonding and grounding relates to ground fault protection. In that one of the reasons that specific ground fault protection was required back in 1971 was because the standard overcurrent protected devices, i.e. fuses and thermal mag circuit breakers, were not effectively protecting against arcing ground faults. The principal reason for that is because there were too much impedance in the ground fault return path. And we can reflect back on the chart we showed you earlier as to what happens as you go up in size with circuit breakers, size or fuse. What is the maximum impedance that has to be what is the maximum impedance that's allowed in the ground fault return path? What you see is as you go up in ampacity of overcurrent protected device, the maximum amount of impedance in the ground fault return paths must dramatically be reduced, just such that the device will operate in its overcurrent protected device state, not its thermomagnetic, not its magnetic state. For example, overload devices for fuses and circuit breakers operate in a certain time band, a long time, an overload. And that's exactly what was happening with fuses and circuit breakers during a ground fault condition. You had an arcing ground fault where the system was emitting quite a bit of current. But because there was a lot of impedance in the ground fault return path, the breaker did not operate in its magnetic functions. It operated in its thermal functions, which took a long time for the fuses to open or the circuit breaker to open. Consequently, you allowed a lot of energy to be dumped into a fault, and fires resulted. So the industry acquired something a lot more sensitive to this device, more sensitive to ground fault protection, and hence the ground fault requirement in 1971. Let's take a short break. Get into multiple systems. All right. As the industry converted to solidly grounded systems, there was an issue with high fault currents. One of the ways to mitigate that was the use of resistors in the exo circuit to limit the amount of fault current. Basically, we spoke of earlier having a low impedance in the ground fault return path in order to facilitate the operation of the overcurrent protected device, and also the requirements for ground fault protection. However, there were systems in which impedance is deliberately inserted. Those are called resistively grounded systems. And there are two types of resistively grounded systems. There are low resistance grounded systems and high resistance grounded systems. These were primarily initiated by the petrochemical and the pulp and paper industry. Because the industry was converting to solidly grounded systems, or three-phase 4 wires, those type of industries are very, very sensitive to arcing ground faults, where traditionally they had employed ungrounded systems, and in some cases still do. But they also saw the benefit of using three-phase 4-wire systems as a means of providing 277 for their lighting inside their facilities, or to operate their systems in general. It cut down on cost, installation. However, they were also concerned about the magnitude of fault current that resulted from solidly grounded systems. So they began to convert a little bit. They changed the power system configuration such that they deliberately inserted resistors in the exo circuit to limit the fault current. Again, which is exactly the reason that fuses and circuit breakers didn't operate. Now that you have devices that can sense lower levels of ground fault current, they can get the benefit of having ground fault protection as well as limiting the fault current. Hence the introduction of what they call the low resistance grounding system. You are actually injecting or installing a resistor in the return path between the exo bushing of the supplying transformer and the ground plane, such that you can limit the fault current. If you assume that the impedance is very, very low between the point of the fault by having an effectively bonded system and to the point where you connect to your resistor at the exo of the transformer, then you can limit the flow of current going